can you please share your screen?
Yes. Okay. Good afternoon.
Okay.
Can you see my screen?
Yes. Very good. Okay, so we can go on with the next speaker, who is Stefan Nonnenmacher, and he will talk about the localization of chaotic eigenmodes. So please go ahead.
Okay. Thank you. Thank you, everybody. Thank you for the invitation. It's a pleasure to come back, well, let's say virtually to IPhT after a few years. So my talk will appear maybe as coming from the prehistory of quantum chaos. So I'll speak about very easy, simple objects to look at. It will be less discrete and more continuous. So I will focus on the structure or what can be said about eigenstates of the Laplace-Beltrami operator or Laplace operator on certain Euclidean domains or certain manifolds, Riemannian manifolds with chaotic behavior. So this is a very standard topic in quantum chaos. So here I plot, for instance, on this page, I just plot some some eigenmodes of some hyperbolic surface. Okay, these plots were provided by Alex Strohmeyer. Okay, so here you can see that you go to higher frequency when going to the right. So this is the setup. Okay, the easier setup is to look at drums, Euclidean drums or Euclidean domains of quantum billiards. You can call them different names, and assume that you take Dirichlet boundary conditions on the boundary. Okay, these are deformations of a circle. This is a circle. This is deformation, which is a limaçon. And then when you deform again to the end, you get a singularity, and this is a cardioid. And this one is chaotic. This one is not chaotic. It is let's say intermediate. And this one is, of course, is integrable. So we know that the Laplacian has a discrete spectrum, and we want to say something, whatever, about the structure of these eigenmodes. Okay, and what we will be looking at, high frequency modes, okay, which is equivalent to looking at semiclassical regime, the semiclassical regime of quantum mechanics, okay, where this Laplacian times h squared is the kinetic energy of a quantum particle. Okay, you can view this as a quantum particle traveling inside this cavity. Okay, and the Planck's constant here is an effective Planck's constant, which is just the inverse of the frequency. So I will recall, of course, I think most people know about semiclassical quantum mechanics, but I still recall what the type of method which we'll be using. So in this semiclassical regime, when the Planck's constant is very small, so here I remove the mass of the particle. So the mass is equal to 1, if you want. So semiclassical regime is that h bar is small compared to 1. Okay, in my let's say a dimensional units. Okay. So there is a connection between Schrödinger dynamics, Schrödinger equation, and time-dependent Schrödinger equation, and ray dynamics or classical dynamics, if you want. Okay. And one manifestation of this connection is by looking at the evolution of wave packets, of Gaussian wave packets, which you can call coherent states. Okay, so it's a Gaussian. I didn't give the formula. I guess it's a standard Gaussian wave packet, which is localized initially at the point x naught and with momentum p naught. Okay, and this, of course, there is an h bar. It depends on in the formula for this wave packet. This wave packet depends on h bar, of course. Let's say it's localized here. What semiclassical mechanics tells us is that when you propagate it through Schrödinger equation, it will propagate along the classical ray, okay, the light ray, if you want. Except when you hit the boundary, then it is reflected according to the standard specular reflection rules. Okay, so you follow for a while the classical dynamics, the classical ray dynamics, and there is a second effect, which is a form of dispersion or squeezing. That is, if you start from a minimal uncertainty wave packet here, after it propagates, or even during the propagation, it will disperse a bit. It will widen. It will get squeezed or deformed, and this is all the more the case when the dynamics will become unstable. When the classical flow will become unstable. So I will come back to this. Okay, but the first approximation, you follow this wave packet, which is microscopic, so it has a width of order square root h bar. It propagates and along the classical ray. So this means that if we want to analyze stationary modes, so stationary modes are modes which are not modified by the evolution, by the Schrödinger evolution, okay, except by a global phase. we need to understand, we need to control the dynamics, the geodesic flow, the classical dynamics. Okay, so we need to have information about the geodesic flow. So there are two limits. Okay, there's one limit which is the semi-classical limit or high frequency limit, and there is, because we're looking at stationary modes, the second limit is the long time limit of the evolution, and these two limits are really, they're not commuting with each other. Okay, so you have to be careful on how you take the both limits. Okay, but the upshot is that we first, to understand this structure, we need to understand first the classical dynamics. Okay, and okay, stationary modes are invariant structure of quantum mechanics or wave mechanics, if you want. And what are the structure, the invariant, time invariant structures of classical mechanics? So point, of course, a point in phase space is not invariant because it moves. So structures are subsets of the phase space. So the phase space is the unit energy shell, if you want. Okay, I call it S star omega. So S star is just notation for unique cotangent bundle in mathematics, but this is just the unit energy shell. Okay, of inside this cavity. So invariant structures are subsets which are invariant by the flow. Okay, so conserved subsets. So the easiest possible subsets are periodic orbits. If you have a periodic orbit, of course, it's invariant. And you have, and then a bit more with more detail, you can construct, once you have a subset, an invariant subset, you can construct an invariant measure, or sometimes many invariant measures, which are probability measures and which assume to be invariant through phi t. Okay, so it can be seen as an invariant cloud of points. So these are the, let's say, the classically invariant quantities. So let's focus now on, because, okay, this is a workshop on which contains the word quantum chaos. So let's talk about chaotic cavities. So chaotic cavity means that the geodesic flow or the ray dynamics is chaotic. So chaotic means that for almost every initial point, the trajectories are unstable. So here, for instance, there's a picture where I start by showing two trajectories starting from the same point, but with very, very nearby angles, initial velocities. Okay, at the beginning, you cannot see the difference. And after a few bounces, you can see that the trajectories completely separate from one another. So they lose the memory that they were close together at the beginning. So this is a manifestation of hyperbolicity, or if you want, the fact that we have positive Lyapunov exponents. Okay. So you can see here. So this is here. This is the billiard, the chaotic billiard, the famous Bunimovich stadium billiard, which was proved to be chaotic by Bunimovich. So this type of, and here this is not a model which I speak at the end, which are manifolds. Okay, so Riemannian manifolds, so which are not flat like the billiards here. They're not flat. They're curved and they have negative curvature. And because of negative curvature, the trajectories are automatically unstable. Okay, they diverge exponentially from one another. So here again, you see two trajectories which split from one another pretty fast. Okay, so from this exponential instability, one can show that there are invariant, that there are periodic orbits, and therefore that there are also many possible invariant measures. So let's say the easiest invariant measure, the most natural one is the Liouville measure, which is here like the Lebesgue measure, if you want. Okay, which is the physical, most natural physical measure, which is invariant by the flow. Okay, because this is a Hamiltonian dynamics, it is conservative, so it preserves this Liouville measure. There are invariant measures located or localized on periodic orbits, and you can also construct more complicated measures, which are fractal measures. And these fractal measures, they can be supported on the full energy shell, or they can be supported sometimes on a proper fractal invariant subsets. Okay, so there's really a zoology, a zoo of invariant measures for such systems. Okay. And essentially due to the exponential instability, to the let's say large number of infinite number of periodic orbits, of hyperbolic periodic orbits. So from this property, from this instability property, hyperbolicity property, one can prove for these systems, one can prove the ergodicity of the flow. So I recall what I mean, probably this is not useful for people in the audience, but I recall the definition of ergodicity, the classical definition of ergodicity here. Okay, just the fact that if you have observable, if you average the observable with respect to time, fixing the initial position, then this converges to the space average, okay, of the same observable for almost every z initial point. So z, the point z's are the point in phase space. Okay, the unit energy shell. You have also property of mixing, okay, which is the decay of time correlations, which was, let's say, alluded to in the previous talk. Okay, and most of some of the results would concern all these systems. some of the results will be focusing only on this model, the geometric model. Well, the reason is that here every orbit is unstable. There is no difference. Whereas for this stadium billiard, for instance, there is a family of orbits which are vertical orbits here, so-called bouncing ball, which are not exponential, which are not unstable, which are marginally stable. Okay, and they play a role. For instance, in the mixing property, the decay of correlations for this billiard is slower than for such a manifold. Okay. All right. So this manifold has somehow the most chaotic possible systems. Okay. The strongest chaos possible is this Anosov property, the fact that every trajectory is unstable. Okay.
Sorry, I have one question, quick question.
Yes. Sure.
I didn't get why the existence of a large number of invariant measures is due to hyperbolicity. This I didn't get.
Well, actually, the way it's made, the way it's constructed, where there are various ways to construct invariant measures. So one way is to start to consider all periodic orbits, and there is an infinite set of periodic orbits, and somehow the structure of the periodic orbits and the large number can be constructed using hyperbolicities. Somehow you can play with short orbits. You can try to play with short orbits and try to modify them a little bit. You get a long orbit. Okay, so there are theorems about shadowing lemmas. It's called shadowing lemmas. So from a bunch of short orbits, you can cook up a longer orbit. So this way you can construct many long orbits. So you can count somehow the number of long orbits, and somehow playing again with these long orbits, you can have measures which are located on these long orbits, which are supported on these long orbits, and then you can start to take linear combinations of these measures and show that. By taking limits, okay, by taking weak limits, that is limits in the sense of probability measures, you can construct measures which are now not supported on a single orbit, but on a more complicated set. So that's one way to construct these fractal measures. Okay, start from long orbits, okay, bunches of long orbits, and take linear combinations, and you don't even need to take linear combinations. You can take some specific families of longer and longer orbits and look at the limit. Okay, inside this family, and this way you can construct complicated measures. Okay, so that's one way. There's another way.
The existence of large variety of invariant measures is more generic, right? I mean, it also applies to systems which are mixed.
That's right. Yes, exactly. So I will not speak about the mixed dynamics systems because somehow they're much less understood. But I agree that for mixed systems you also have many types. I mean, many different measures. But here, all the measures they are supported on pieces of parts of phase space which are unstable because everything is unstable. Everything is hyperbolic. So when you have a mixed system, you have parts of phase space which are, let's say, more regular, okay, and parts of phase space which are ergodic, okay. And so this makes a sort of difference. But okay, I will not. Well, I did not plan to mention. They also maybe at the end I will talk about it. There are also interesting results for certain mixed systems. Okay. Okay, there are some nice things. Okay, so what I will focus on in my talk are the macroscopic properties, macroscopic distribution properties of eigenstates. Okay, and macroscopic means that I fix a subset like this square here, if you want. Okay, I fix it, and I look at the distribution, the mass of the eigenfunctions inside this subset, and this subset is independent of the frequency. Okay, so therefore, since the wavelength goes to 0 when I go to the high frequency limit, the wavelength becomes much smaller than this than the subset here. Okay, so I fix the and somehow I'm just looking at the macroscopic weight distribution of or if you want mass distribution of the eigenmodes. Okay, and so for the first result in this and the most general result in this topic is the theorem of quantum ergodicity. Okay, or it's called also Schnirelmann theorem. It dates back to the 70s, I think, for Schnirelmann, and then it was somehow the proof was not complete, and it was completed by Zeldich and Colin-Verdier in the 80s. Okay, and this theorem states that for almost every eigenstate, when I say almost every, I mean that there is a sequence inside the integer numbers, a sequence of density 1, which means that if you take a large number n, larger threshold n, then the proportion of states which are inside this subsequence is going to 1, it's converging to 1. So this is what we mean by density 1. It means almost every eigenstate. And there is such a sequence such that inside this sequence, the probability densities corresponding to the eigenfunctions they equidistribute, but they equidistribute at the macroscopic scale, of course. They do not equidistribute at the microscopic scale, because at microscopic scale, there are oscillations on the wavelength scale, of course. Okay, these oscillations, they do not disappear, they become thinner and thinner. But if you just look at macroscopic scales, these densities converge to unity. Okay, they become flat. So this is what we call equidistribution, and this is what we call quantum ergodicity. Why this name quantum ergodicity? Because the proof and the property only depends on the property of ergodicity of the flow. So actually, it does not depend on the exponential instability of the trajectories. For instance, it is more it is very robust result. Okay, so it was adapted to many different systems, and it states so that asymptotically along this subsequence of eigenstates, asymptotically the mass, the quantum probability, if you want, inside this region A converges to the volume of A. Okay, normalized by the full volume of the manifold. Okay. So that's quantum ergodicity on the on position space, and actually you also have uniformity in momentum space, that in the Fourier space. Okay, so one way to view this equidistribution in Fourier space, or therefore globally in phase space, is to, instead of using such characteristic functions, that the multiplicative operators here, this is just multiplication by the characteristic function on the set A. You can take a classical observable and quantize it, okay, quantized by standard quantization into an operator, which you have to adapt, of course, the Planck constant in this quantization. It has to be adapted to this eigenstate. And these matrix elements, this diagonal matrix element, converge to the classical average, that is the phase space average of this observable. So we have sorry?
This, for example, applies to a square billiard, no?
No. This will apply to a square billiard, at least to a rectangular billiard, because for squares there are tricky things, because squares have a large multiplicity, so they can have large multiplicity, so things are tricky. But if you take a rectangle with, for instance, irrational aspect ratio, then the first part will apply, of course, because you know that the cosine or the sine functions,
sure.
These will apply, but not this. Okay, this will not apply, because here, for instance, you can decide that this function focuses in some momentum direction, and of course, in momenta, the plane waves in momentum, they are very focused. They are not equidistributed.
I see. Yes.
Okay, so there's a difference between this property, which is true indeed for rectangles, and this property, which is true for ergodic billiards. Okay. So, okay, here it's maybe a bit technical. I just want to mention things about some elements of the proof of quantum ergodicity. Okay, so this proof, quantum ergodicity, deals about almost every eigenstate. So let's say it's an average result, or if it's a result in probability among all possible eigenstates. So it is computed by looking at the moments of these sets of matrix elements. So you look at these matrix elements, okay, along the sequence of eigenstates. All the sequence. Now you don't have to restrict it to a subsequence. You take all matrix elements and you look at the moment, the first moment and the second moment. So the first moment, actually, so this average is like a trace, if you want, a trace of this operator traced over this first family of eigenstates. This converges. This is called local Weiss law. Okay, it's a standard result. It works for every manifold. Okay, every domain or every manifold. It converges to the volume of A over volume of M. So it's a result somehow about the fact that the eigenstate they pile up inside the phase space. Okay, so this is very general to all manifolds. And the second part, if you want to look at how these are distributed around the classical average, you look at the variance. Okay, and you get this expression, which is called the quantum variance. And this is what you want to understand. I mean, to show that these guys converge, most of these guys converge to this thing here. You have to show that this variance goes to 0. Okay, and so this is indeed what you can do. And to do that, you use the semi-classical correspondence, which again holds for every manifold. Okay, it's just the fact that when you take let's say an observable here, generalized an observable, I don't take just these multiplication operators. If you propagate by the Schrödinger flow, of course, you can propagate here the eigenstate. When you propagate the eigenstate, you just get a phase. Okay, you get the phase and here the inverse phase, so it gives you the same thing. So you can by duality, you can put the propagators along against the observable, the quantum observable, and the semiclassical correspondence tells you that at least the time is not too long. This operator here is approximately the same as the classically evolved operator quantized. Okay, the quantization is this hat. Okay, it's a physics notation. So it's the same as, is approximately equal to the quantization of the classical evolution. Okay, this is the semiclassical correspondence. And then if this is true for a time t, this is true for any time t between 0 and capital T, and therefore you can take the average with respect to the time. Okay, so this is why you get also you have the right to take the average with respect to time. And here you start to be in business, because this is here, this operator here, or this function here is the Birkhoff average, okay, of the operator A. So now you can start to invoke, you can start to think about ergodicity, and you can play with ergodicity. So I don't give the last details, but here you have to use ergodicity. And this allows to show that this variance goes to 0 when n goes to infinity. So here you are playing with two limits again. One limit when the time is going to infinity. Okay, capital T goes to infinity. This is what you need to use ergodicity. And you have a limit of semiclassical limit, which is when n goes to plus infinity. So you're doing the two things. But here you first do the limit, the semiclassical limit, and then the long time limit. You do it in two different steps, okay, which means that the large times here remain independent of h bar. You don't have to take times depending on h bar. Okay, so this is what we know. This is a quantum ergodicity. So another way to view it is to look at the Wigner distributions associated with the eigenstates. So Wigner distribution or Wigner functions, they are functions in phase space, okay, which you construct from eigenstates. And one way to express quantum ergodicity is to say that these Wigner distributions converge in a weak sense, in a distribution sense or in measure sense, converge to the Liouville measure, okay, this natural invariant measure. Okay, and so here so far, quantum ergodicity tells us that I have to do, this is the case if I take this density 1 subsequence. So natural question is do I need to take this subsequence, or does it hold for for the full sequence? Does it, or are they on the opposite? Do they exist exceptional eigenmodes, eigenstates, which do not have this flat, asymptotically flat behavior? Okay. Anyway, even before quantum ergodicity, we know one fact is that if we look at this sequence of Wigner distribution, if we extract the subsequence, we can always extract a subsequence which converges to something, to some measure, and just do okay, mathematically it's called weak compactness. Okay, so the fact that when you take limits of measures, of probability measures, you can extract something. You can take subsequence which converge. Okay, and so what can it converge to? It converges to probability measures which are first supported on the unit energy shell. Okay, and these probability measures are invariant. Okay, these are a property which you prove easily also using the semiclassical correspondence, that the limit measures must be invariant. So these limit measures, they are called semiclassical measures. They embody the large frequency behavior, large frequency distribution of some subsequences of eigenstates. Okay, so that's a mathematical way to describe families of eigenstates, high frequency families of eigenstates. Okay, how these eigenstates distribute over the unit energy shell. Okay. And so the question now is what are these semiclassical measures? So what measures appear by taking subsequence? So quantum ergodicity tells me that if I take this sequence here, this sequence converges to mu L. Question: do there exist other sequences, okay, which are necessarily scarce sequence? There will be density 0. There will be very few, very scarce eigenstates, which could converge to a different limit, which means that these eigenstates have different behavior. So there is a conjecture which was expressed a long time ago, also by Rudnick and Sarnak, which focus on manifolds of negative curvature. Okay, and their conjecture is that there is no exception. Okay, because they could not pinpoint any exception, so they say, okay, well, probably there's no exception. So all eigenstates should behave like this. So this is called quantum unique ergodicity, and this conjecture has proved to be to resist more than people expected. Okay, so so far it was proved for very few systems. So it was proved by Lindenstrauss for a certain family of hyperbolic surfaces, that is surfaces of constant negative curvature, which have also arithmetic symmetries. Okay, so here arithmetic symmetry means the existence of a family of so-called Hecke operators, okay, which are operators which are some discrete Laplacians, which commute with the Laplacian, with the standard Laplacian. Okay, they all commute together, so they form a commuting family of operator. And so you want to diagonalize them simultaneously. And this is what they did, what Linus-Strauss considered. So it considered joint eigenbases, and for a joint eigenbasis, he proved that there is only one possible limit measure, which is the Lebesgue measure. So, all right, but he needs really this symmetry, this very specific symmetry. On the other hand, people already in the 80s had done numerics, and on the numerics, like for the stadium billiard, they saw such things, you know, like what they call scars of periodic orbits. So here you have a periodic orbit, this bounce here, horizontal one. You have here, you have another one, you see, and they've seen these scars, okay, these enhancements, and they say what, well, maybe some eigenstates are, let's say, stronger here, have a stronger let's say stronger mass along these periodic orbits. So here you have a very strong scar associated with this vertical family of orbits. Okay, there's a family of vertical orbits which are called bouncing ball orbits. And so the question was, are these enhancements strong enough to be detected as in probability in some sense, to be detected in the limit measures, or are these enhancements weaker? Okay, so somehow, well, there is still no consensus. I think most people would think that these ones here are too weak to be detected in these semiclassical measures. But again, semiclassical measure is something which it's something which is defined in the limit of high frequency. Okay, limit when frequency goes to infinity. Whereas these plots, these numerics, they are done at a fixed frequency. You know, cannot go to infinity. But still, you can go pretty high. Okay. So so far, the only theorem I know is the theorem by Hassel, okay, Andrew Hassel, who proved that for this stadium billiard, actually, there exist semiclassical measures which carry some part of this, which carry some part of these bouncing ball orbits. So which are singular with respect to, which contain a singular component with respect to Lebesgue. So it is not just Lebesgue. So he proved that for this billiard here, there is no quantum unique ergodicity in some sense. Okay. So that's the only result against quantum ergodicity for this type of dynamics. And okay. So far, that's the only one. So we don't have any proof or disproof of quantum unique ergodicity for manifolds of negative curvature. So we'll still try to say something, okay? And so why do we expect delocalization? We expect delocalization because if you look at wave packets, Gaussian wave packets, okay, and you evolve these wave packets, then you can analyze this evolution of wave packets rigorously, and these wave packets will spread. Due to the hyperbolicity of the flow, of the classical flow, the wave packet will spread, will be deformed, and it will be deformed exponentially fast. Okay, and so if you look at the numbers here it goes like e to the lambda t. Lambda is the local Lyapunov exponent, if you want. Okay, so after some logarithmic time, which is called the Ehrenfest time, okay, some multiple of log h, log 1 over h, this state, this initial microscopic state, will delocalize, which means that it will become macroscopic. Okay, it will spread along a piece of unstable manifold. And if you go to longer and longer times, this piece of unstable manifold will spread and will wrap around the energy shell. Okay, and it will wrap more and more densely. It will converge in a weak sense. It will converge to the Lebesgue measure, to a Liouville measure. Okay, so individually for one of these coherent states, when you expand it by time, it will spread and converge to the Liouville measure. So we know that an initial state, an initial coherent state, an initial eigenstate can be expanded as a sum or integral of a coherent state. So if each of these coherent states spreads by time evolution, what happens to the sum of these states? Well, actually, because these states, you know, they're not positive densities. These states, they are states which they're complex valued. Okay, so actually they can interfere. They can have interferences. That is, they can be cancellations, partial cancellations between several terms. Okay, so the delocalization of individual states does not suffice to prove the delocalization of the full guy. Okay, so of course this is not the proof does not work like that, because this would be a proof of quantum unique ergodicity, but of course due to interferences this is not does not work. Anyway, I mean, this control of this coherent state of these wave packets beyond the Ehrenfest time, that is for longer logarithmic times, is crucial in the proofs of the two results I will show below. I will not show. So these results, they do not prove quantum unique ergodicity, but they still put some bounds, okay, put some constraints on the possible semiclassical measures, that is the possible behaviors of high frequency eigenstates. So the first result, which was obtained already a 15 years ago, okay, consisted in measuring the delocalization, or measuring somehow quantifying the, let's say, the spreading of the measures, of the semi-classical measures, by using one invariant which is called the entropy, the Kolmogorov-Sinai entropy of this measure. So Kolmogorov-Sinai entropy is a number of positive or non-vanishing, positive or non-negative number, which somehow measures, let's say, the complexity in the sense of information theory, complexity of some invariant measure. Okay, so to do it, you have to start from a partition. You have to partition the phase space, actually not just the manifold, but the phase space. Okay, you know, it's like when you go to the butcher, you have pieces. You can see pieces of the cow, different pieces of the cow. So you partition here your manifold, and you just record in which piece is my point when I start from point. In which piece is my point at each integer time. Okay, so this gives you a set of numbers, a sequence of numbers, a word, an infinite word, if you want, associated with your initial point. Okay, and somehow the entropy tells me how much information do I receive about my initial point, how much extra information do I get when discovering the next piece, when discovering the next number. The next number means where is my point, in which part is my point at time n. Okay, so how much information do I get compared with the time n minus 1. So it gives you some idea of the spreading of the measure, of the invariant measure among the little pieces, not just the initial pieces, but also the pieces which you get by refining the partition. Okay, so here E with the E subscript boldface K, big K here, corresponds to E subscript K1, K0, Kn, corresponds to the points which are in the set ek0 at the time 0, in the point in the part ek1 at time 1, in part ek2 at time 3, etc., etc. So this piece becomes smaller and smaller. Okay, and so you look at the distribution of the mass in this on these refined partitions. Okay, and somehow the growth rate of these entropies here, you look at the entropy, Shannon entropy of this. This gives you the Kolmogorov-Sinai entropy. So the theorem, which was proved by Nonnenmacher, and then another one was proved by Nonnenmacher, Koch, and myself, is that for any semi-classical measure, the entropy is positive. Okay, and in constant curvature, it's even more precise. You can get some explicit number. Okay, so so this positivity of the entropy tells you that the semi-classical measure cannot be too thin. Okay, they have a support which is sufficiently thick in the sense of fractal dimension. So it can be a fractal set, but it cannot be too thin a fractal set. Okay, so that's first result. That was a first result. So which excluded, for instance, the measures supported on periodic orbits. Okay, they have to be thicker in some sense. Okay, and the second result I want to mention also is the result which was obtained much more recently. So it was first obtained in constant curvature surfaces. So it's a two-dimensional result only. It applies so far. It applies only in 2 dimensions for surface of negative curvature. So it was proven in constant curvature first by Dyatlov and Lin, and sorry, it's not Lin, it's Jean. I'm sorry, I make a mistake here. And also I contributed to the generalization to variable curvature. And so the result is that all semi-classical measures are fully delocalized in the sense that the support of the measure is the full phase space. That is the full energy surface. They cannot be supported on a strict proper fractal subsets, okay, invariant subsets. So it's a slightly different result compared with the one on the entropy. Okay, it does not improve the result on the entropy. It's something orthogonal to it. Okay, but it applies only to compact surfaces. And so the idea is that the upshot is that to each subset of your manifold there is a positive number, positive mass if you want, and any eigenstate will have a mass larger than this positive number. Okay, whatever you go, whatever high the frequency. Okay, so you cannot concentrate away from some part in phase space. Okay, so this is what I call full delocalization. Okay. So I will just scan, let's say because I'm late, I will scan the idea of the idea of one tool which was used in this proof. It's a tool which was discovered by Bourgain and Dyatlov 5 years ago. It's called a fractal uncertainty principle. Okay, so one fractal uncertainty principle is an uncertainty principle because it tells you that an eigenstate and its Fourier transform cannot be simultaneously essentially localized on fractal sets. Okay, so one way to express this is to look at two fractal sets x and y on the unit interval, thicken them to the Planck scale, or to the let's say wavelength h bar. Okay, thicken them to this Planck scale, and so you get this x of h bar, y h bar, and look at operators which are just these operators just let's say operator of characteristic function multiplication operator by the characteristic function on this set, and here the same on the Fourier side. Okay, it's just after Fourier transform, after semiclassical Fourier transform. The product of these two operators will be small. Okay, that's the result. Small means that it is some positive power of h bar. Okay, so it cannot be of order 1. The impossibility of having this operator of order 1 means that there is no state which is essentially localized on x of h, such that its Fourier transform is essentially localized in y of h. And this result it's not a question of volume. Of course, these sets here, they have microscopic volume or microscopic length. If you take the full length of x of h, it is microscopic, but it can be still larger than square root h. Okay, and the length of y of h can be larger than square root h as well. And so if you put an interval of length square root h here and square root h here, you can fit in a quantum state. You can fit a coherent state. You can fit a Gaussian wave packet. A Gaussian wave packet is localized on scale square root h. So here you can have fractal sets which have a total length much larger than square root h. It's impossible to fit in quantum state. So somehow the proof really uses the fractal structure of the sets, the geometry of the set, and the fractal structure means that there are holes at every scale, from scale 1 to scale down to scale h. There are holes at every scale. Okay, it's called porosity. It's a porosity property. Okay, and once we have this theorem, okay, the fact that you cannot fit in a quantum state in this both in this set and such that the Fourier transform is fit in this set, you can somehow view this as a model. Okay, these two fractal set, you can view it as a model of unstable versus stable manifolds. Okay, so stable and unstable, they're not exactly horizontal and vertical, but you can somehow deform them to be a horizontal, almost horizontal and almost vertical. You can play a bit, and somehow this object and the intersection here of the green, of the blue and red pieces, they could be a model for some fractal invariant set. Okay, so in some sense here you see that you cannot fit in a state on this fractal invariant set. Okay, well. So this is a very sketchy idea of the proof, but I wanted to emphasize this nice, let's say, new uncertainty principle, type of uncertainty principle. Okay, so this is now this is my last slide. So there are other questions, of course, which people can address. So about quantum ergodicity, I looked at the macroscopic distribution. There are, let's say, more recent results, like about 5 years ago, started 5 years ago, but quantum ergodicity at the microscopic scale or small scale. But the small scales are not so small. Okay, they are the scales of the order of log h to the minus alpha. Okay, so this is not so small. Of course, this is much larger than the wavelength. Okay, so it still contains many wavelengths. But you can prove some equidistribution at this range of scales. Okay, so now things which are now more away from mathematics and more into theoretical physics is what happens if we zoom at the scale of the wavelength, and then we enter the realm of Berry's conjecture about random wave model, monochromatic random wave model. Okay, so Michael Berry conjectured that for these chaotic states, if you look at them statistically, they look like a random wave. Okay, but so far there's no, as far as I know, there's essentially no result about that in this setup actually. So, well, there are some results, some interesting results connecting quantum states with some random waves, but they're not eigenstates. Okay, so these two people, Angromo and Rivera, they took WKB state, okay, that is like a plane wave, and they evolved it on such a manifold of negative curvature. They evolved it, and they show that almost surely at most points, near most points, if you evolve long enough, then the state looks like a bit plane wave in some sense. Okay. That's a result they obtained here, but this is not for eigenstates. Okay, going to eigenstates is really very hard, I guess. Okay, and I want to mention also a large activity which was along these ideas. Okay, if you take now for granted this model of random wave, monochromatic random wave, people have looked at statistical properties, including the nodal set. Okay, the nodal domains, the nodal set of these of these functions, of these random functions, and Okay, there were two papers in the early 2000s which really spurred a lot of activity in the math probability community. Actually, so I did not quote everybody, but I quote the two original papers which somehow had large impact in the mathematics mathematical probability community, I would say. And finally, I mentioned that everything I told about is about one body system, okay, one particle in the billiard. So of course, what happens when you take n particles and you try to start to couple them, it's another matter. Okay. All right, thank you for your attention, and I'm ready for questions, if any. Thank you.
Okay, so thanks a lot for the nice talk. Let's upload to the speaker. We are a bit late, but let's have a couple of quick questions. So please unmute yourself. Okay, Alessio.
So I was trying to understand the implications of the results you showed for scars. So do I get it correctly that this means that Heller scars don't belong to this strict semi-classical limit? I mean, this high frequency.
Well, at least I mean, what is believed, I think, now is that Heller scars, which are these ones, which are the ones associated with unstable periodic orbits, that is hyperbolic periodic orbits.
Yes.
Not this one, but this one.
Yes.
Probably you don't see them in the limit when you look at the L2 mass like we do here. That is, when you look at when you look at let's say a little piece, let's say. If I look at the little piece here, well, it's not so little, but you know, and you try to look at the mass, the L2 mass, when you go to high frequency, the belief is that you will not see that, at least in the limit of the semi-classical measure. So Heller had some theory. He started to look at fluctuations. He said, okay, let's look at a family of such states and look at do we deviate? Do we deviate from the flat limit, and how much do we deviate? So he looked at the fluctuations of. He had some conjectures about the fluctuation of these mass compared with the fluctuation for a random state. So indeed, I mean, these states, they do not. If you look at them visually, they do not look like random. But the question is, does this? It's not clear. Apparently, this mass is not enough. Even if there are enhancements, these enhancements go to zero. Let's say will not be seen in the high frequency limit. So there could be more finer ways to measure these enhancements. Okay, so maybe instead of looking at the local L2 mass, you could look at L4 mass, L infinity, for instance. Look at the subnorms of these states and wonder whether the subnorm along this orbit is larger than what you expect for random states. So you really want, the thing is that you want to compare some statistical measures of fluctuations. You want to compare them with the random states. Okay, you want to see this is not just a random state, but this is something which has a stronger. So in the sense of L2 mass, which is what I did here, and which is what semi-classical measures are about, the belief is that these enhancements here disappear in the high frequency limit, but they could remain if you look at different types of measures. Okay, like LP norms or L infinity norms. Okay. So, you know, Heller at his time was not going to very high frequencies. Okay, so then people managed to get higher and higher frequencies numerically, which is not trivial task. Okay, and somehow when you look at higher frequency states, you don't see it somehow so much enhancements. You see some sign. You see already here, this one is a bit thinner, fainter than the one here. Okay, so
you see this in numeric. You see that it becomes fainter.
Yes, when you go to higher. Yes, I think they managed to go to the 30,000 states or things like this. Somehow you see the shape from far away. You see the shape, but you know, maybe your eye is very well trained. Your eye is well trained to detect such images. But when you look at purely basic mathematic objects, it's not so easy to see whether to compare it with a fluctuation, which is just a random fluctuation. Okay, because you know for a random state you will have also fluctuation. Okay, you will have some. So it's an interplay between fluctuation and propagation. Okay, so Heller had some let's say some ideas, some theories, but okay, they were not mathematically let's say plain, I would say, rigorous. But he had some idea, you know, mixing somehow propagation of wave packets and looking at fluctuations. So okay, so looking at the tails, for instance, of the mass. And the tails in the sense that the points where the local function is the highest. Okay, look at the tail of the distribution, of the value distribution. Do I see something different if I put myself on a periodic orbit or not? Another complication, of course, is the fact that there exist periodic orbits everywhere. You know, I mean, the set of periodic orbits altogether is dense on the billiard. So in some sense, every point, near every point, you have a periodic orbit. But of course, you have a very long periodic orbit. So the question is, do we see only the short ones, and why do we see the short one? And what is a short one? What is a long one? In some sense. So that's also another difficulty. Okay.
I get it. Okay, thanks. Thanks a lot.
Mm-hmm.
Okay, any other question? I think we only have time for the last one. If not, I will ask a quick question. So just a relation about your talk and the one that we had previously. So, I mean, one important object of the previous talk was the spectrum for factor. And I know that there were works by Barry trying to explain why there is a connection with the random matrix theory.
Yes.
So I wanted to understand how mathematically rigorous is this. So we know for sure that for billiards, for instance, K equal T or...
Yeah, yes. Okay, so I mean, Barry had performed this diagonal approximation. Okay, so as far as I know, I understand diagonal approximation is valid, I think, rigorously, but only for okay. Sorry. So I mean, the random matrix conjecture tells you that K of T is equal to T. Or maybe, well, this is here the billiard time reversal invariant. So it's not, it should be the COE, the GOE picture,
yes.
but the GOE picture should be valid on the scale of the Heisenberg time. Heisenberg time here is 1/h bar. Okay, so let's say that. So you expect this COE picture on the scale of the Heisenberg time. Okay, 1/h. And if you want to look at rigorously, you can control somehow the diagonal approximation. You can control it up to the time log 1/h, okay, which is much shorter, which is this, sorry, Ehrenfest time in some sense, or maybe some multiple of the Ehrenfest time. Okay, so you have a control, semi-classical control on this diagonal approximation, at least the way I understand it, up to that time. And now, if you start to go beyond that time, the problem is that you have lots of terms. You know, when you look at all the possible orbits, you have an exponentially growing set of periodic orbits. And because I mean, Barry's method starts from the trace formula, from Gutzwiller trace formula, and looking at pairs of orbits. Okay, and so the fact that you have a proliferation of periodic orbits tells you that when you go beyond this Ehrenfest time, the number of orbits is exponential. So okay, well, if you go to the time 1/h, the Heisenberg time, the number of orbits is exponential of C/h, which is something you have no way to control rigorously, okay, because you have much too many orbits. So of course, after Barry's work, there was this work by Richter, Sieber, and the group of Hacke, etc. So they understood that it's not just the diagonal ones which matter, but also some pairs of off-diagonal ones, and they identify pairs of orbits which have encounters and which should also be relevant, which are relevant also in this sum. So in this sense, all these people, I mean, it's very interesting and complicated work, but managed to identify pairs of orbits which give you a non-zero result, in some sense, a non-zero contribution to this form factor. But then there are the rest of the orbits. Okay, and this rest is still huge. Okay, and somehow let's say what they think or what they claim is that the rest of the orbits, the one which we did not identify as being interesting, the rest they sum up to zero. Okay. So, but I mean, the rest is still the number of pairs in the rest is still horrendous in some sense. I mean, still exponential of C/h. So mathematically, I don't see a way, I don't see a way to justify that. So that's okay, showing that the non-interesting pairs add up to zero. Okay, that's
okay.
I think.
Okay, thanks a lot. So let's thank again the speaker.
Welcome. Thank you for the invitation.
And this is the end of this session. So I think we start again at 7.
Start again at 7 p.m. Now we're gonna disconnect the Zoom link and we'll resume it a few minutes before 7 p.m.
Okay.
Thank you very much. See you all soon.
Thank you.
Bye bye.
Bye bye.